What is a species? You consider the category FB whose objects are finite sets and arrows are bijections. So we only allow bijections in this category. And let F set denote the category of finite sets, the usual category of finite sets, meaning that the objects are finite sets and arrows are all functions. A species is a functor from FP to F set. And what does this mean? This means that for every finite set U is associated a finite set Fu. And for every bijection sigma from U to V, we have a function F sigma, maybe I'll write it like this, Fu to Fv, a function F sigma. Okay, and you can show that F sigma is always a bijection for every sigma bijection from U to V, and that's because F sigma inverse is F of sigma inverse. Okay, so let's look at an example to just get an idea of what's happening here. So we'll call the A FB to Fu the species of arborescens, which is rooted trees. So what this means, I'll explain. So AU is the set of all rooted trees with vertices labeled by the elements of U. And given sigma U to V and rooted tree T belonging to AU, you define sigma T. This should be a tree with vertices labeled by the elements of V. So this is the tree, the rooted tree obtained by replacing the label U belongs to U by the label sigma U belongs to V. If I want to write this even more formally, what we can say is AU consists of all collections of pairs E comma U, where firstly E is a subset, maybe I should say E is a collection of subsets of size 2 of U. U is an element of U, and this data satisfies certain axioms. E comma U satisfies the axioms for rooted trees. for which I will refer you to any graph theory book. So basically the axioms will say that there is no um, there is no cycle in this graph whose vertices are the elements of U and whose edges are the elements of E. It's a simple graph. Okay, so this example tells us how we talk about species. And so talking about species, we say Fu is the set of F structures on U, and F sigma is the transfer of structure via sigma. And as we've seen in this example here, AU is the set of all possible rooted tree structures on the set U, and F sigma, maybe I should say here F sigma of T, put T in round brackets, is the tree obtained by transferring the structure from U to V using the bijection sigma. Okay, and visually we write it like this. We draw the elements of U as a set, and we depict the putting of an F structure on U with this. So this depicts putting an F structure on the set U. Okay, so let's look at some more examples of species. You can fill in their formal definitions as you please, but these are standard examples with standard notations. So G is called the species of simple graphs. Okay, since this is the first example, let me just elaborate a little bit. G of U consists of just all pairs, all subsets E, such that E is a subset of size 2 of U. So what we're talking about are simple graphs without loops. E is just the edge set, and a graph is completely specified when you give specify its edge set. And given sigma U to V, and let's say a graph gamma belongs to, or maybe I should just call it E, belongs to GU, we have sigma of E is just sigma of S belongs to E. So each of the edges S, you replace it by its image under sigma, which is again going to be a subset of size 2 because sigma is a bijection. And maybe here I should say boxy. Okay, so G is the species of simple graphs. GC is the species of connected simple graphs. So that's the same species GU with an additional axiom, which is that the graph is connected. Little a is the species of trees without a root, and these are arbre in French. D is the species of directed graphs. Par is the species of set partitions. P is the species of subsets. So given U, PU will consist of all the subsets of U. End is the species of endo functions, namely all functions from U to U. Here maybe I should say a word. So given a function f U to U and sigma a bijection U to V, then, so this is in the category end. then sigma f of sigma u is sigma v is the definition of the transfer of structure. In other words, you can write also that sigma inverse, or maybe I'll write it like this: sigma f is equal to sigma inverse f sigma. No, it's sigma of fu. So this is sigma f sigma inverse. Conjugation by sigma. That's the action on end of functions. Inv is so the elements of in view are a subset of the elements of end u, and these are the involutions on u, functions from u to u whose square is the identity. And one example that we'll be looking at a lot is S, which is the species of all permutations. This is also a subset of end, or rather S of u is a subset of end u. C is the species of um, cyclic permutations on u. And last is L, which is the species of linear orders on u. Okay, so these are the standard species that are usually named, and we can talk about the category of species, which is a functor category, the category of all functors from FB to finite sets. Okay, now there's some more examples. So the examples we've looked at above are defined using structures. Namely, you have some names which you interpret in the set U, and you have axioms that they must satisfy. But there's some species you can define more directly. And these are very important when we study the algebra of species. So E, it's French for set, which is ensemble, and E of U is just singleton U, so the set U. So there's only one element in EU, and then there's epsilon, which is elements, and epsilon of U is the set U. Okay, so epsilon of the empty set has cardinality 0, epsilon of a set of cardinality n has cardinality n, it is the set n. You can imagine how transfer of structure is defined here. X is called the species of singletons. In the calculus of species, this will play the role of multiplication by x, and x of u is defined to be u if cardinality of u is 1 and empty otherwise. And then we have 1, which is the empty set, and this is the species which will play the role of a multiplicative unit when we define the calculus of species. And 1 of u is u if cardinality of u is 0, i.e. u is the empty set and empty otherwise. It's a singleton u, so it has one element if you have the empty set and 0 otherwise. So this will play the role of a multiplicative unit. And there's an additive unit which we'll call the empty species. And this is just going to be empty for every set u. And finally, ek is a set of size k. It's like E, but it only recognizes sets of size k. If cardinality of u is k, empty otherwise. Okay, so these are some simple examples of species, and now let me define the basic generating functions that are associated to species. So the first is the exponential generating function of a species. We'll call it the exponential generating series. So if I have a species f, I'll denote this just by f of x. And this is defined as summation n greater than or equal to 0, the cardinality of f of n. So here the notation is f of n stands for f of, well, this box n, where box n stands for the set 1 to n. Okay, but it's an exponential generating function. I divide by n factorial x to the power n. Then there's the type generating series. F tilde x, this is sum n greater than or equal to 0, cardinality of Sn mod Fn. Now I need to say a word here. This is an ordinary generating function. So what you should notice that Fn has an action of Sn. Given sigma belongs to Sn, well, sigma is an element of, it's an arrow from n to n. It's an arrow in the category FB, and therefore we can talk about F sigma. So this is going to be a bijection from Fn to Fn. And this makes Fn, by functoriality, the fact that a functor must respect composition implies that this is a group action. And so Fn is a set with an action of Sn, and what we are saying here is that we are counting the number of Sn orbits on Fn. In the case of rooted trees, for example, this would be the number of isomorphism classes of rooted trees with n nodes. And this is an ordinary generating function. There's no n factorial. We'll come to examples in a moment. And the last but most interesting one is called the cycle index series. And this is given by ZF, and this is a series in infinitely many variables which we call x1, x2 and so on. It's summation n greater than or equal to 0, 1 over n factorial, sum over w in, maybe I'll call sigma in Sn. Now let's take f of n. This has an action of Sn. I look at the fixed points under this, of sigma under this action. Okay, I take that and then I multiply it by x1 raised to m1 sigma, x2 raised to m2 sigma, and so on, where mi sigma is the number of I cycles in sigma. So there are three generating functions associated to species, the exponential generating series, the type generating series, and the cycle index series. The cycle index series is a function in infinitely many variables. Notice that when you take this infinite product here, it's really finite because any permutation sigma is going to be a permutation of S in Sn for a fixed n, and so k of sigma will be 0 whenever k is greater than n for sure. And so most of these exponents except finitely many will be 0, and so this would just be a finite product. So this is an infinite sum, but the monomials here are definitely finite. And we think of these as formal power series. There's no question of convergence. Okay, let's compute these in some examples. So let's just compute it for f equals s, the species of permutations. So given w in Sn, recall that uh, the Sn action. So let's say w in, just to be more clear, Sn. So this is going to be a permutation of the set 1 to n, and the action of Sn is given by sigma acts on w by sigma w sigma inverse. This is as we explained when we defined endo functions, and permutations are a subset of endo functions. So that's the transfer. That's the transfer of structure under sigma. Okay, so let's compute the series. So fx is just summation n greater than or equal to 0, the cardinality of Sn divided by n factorial x to the n. But cardinality of Sn is n factorial, so this is n factorial by n factorial cancels out. And so this is just summation x to the power n, which is 1 over 1 minus x. F tilde x is the summation n greater than 0, the number of Sn orbits on Sn. And here the action of Sn on Sn is by conjugation. So really we are asking for the number of conjugacy classes in the symmetric group. And so this, as you know, is determined by cycle type, and so we get Pn x to the n. And this, you know, by Euler is product I greater than or equal to 1 over 1 minus x power I. And now let's compute zf x1 x2. So this is summation n greater than or equal to 0, 1 over n factorial, summation w in Sn. And then we have to take the set of all permutations on the set 1 to n. We have to take the fixed points under sigma, and then we have to take x1 raised to m1 sigma, x2 raised to m2 sigma. Let's take here sigma. Okay. Now this only depends on the cycle type of sigma. The number of fixed points, it is the centralizer. The number of fixed points for sigma is the centralizer of sigma, and that only depends on the cycle type of sigma. So if we write that, we have summation n greater than or equal to 0, 1 over n factorial, and the cycle types are given by partitions of n. So we have lambda partition of n, and then we know that if you have a partition with cycle type lambda, then it's well, how many are there? So its centralizer is of the form product of I raised to mi lambda factorial, where mi lambda is the number of times I occurs in the partition lambda. And then we have x1 raised to m1 lambda, x2 raised to m2 lambda, and so on. But the number of fixed points is also let's see. So this is just the number of elements with cycle type lambda, but the number of fixed points is again the centralizer. So it's product of I raised to mi lambda factorial. And then finally we have x1 raised to m1 lambda, x2 raised to m2 lambda, and so on. And finally this gives so this cancels off with this cancels off with this, and so what you get is summation n greater than or equal to 0, summation lambda is a partition of n, x1 raised to m1 lambda, x2 raised to m2 lambda, and so on. Now, if lambda is a partition of n, that corresponds to saying that m1 lambda plus 2 m2 lambda plus dot 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 is equal to n. And so we are summing over all n, the m1 lambda m2 lambda satisfying this constraint. But this is just in the same as forgetting about what n is and just summing over all possible non-negative values of m1, m2 and so on. So what we get is mi greater than or equal to 0, product I greater than or equal to 1, xi raised to mi. But interchanging sum and product here using distributivity, we get xi raised to mi, which is product I greater than or equal to 1 over 1 minus xi. So what we get here is, so let me just put this. So what we've computed is, yeah, maybe I shouldn't say f tilde here, I should say s tilde here. We're talking about s, and we have z s tilde of x1, x2 equal to product I greater than or equal to 1 over 1 minus xi. So here we have here all the three different generating functions for the species S. The exponential generating function is 1 over 1 minus x. The type generating function is product 1 over 1 minus x to the power I. And the cycle index generating function is product 1 over 1 minus x subscript I. So notice that the only difference between the type generating function and the cycle index generating function is that x subscript I has been replaced by x superscript I. And this actually turns out to be a usual feature. In fact, if you know the cycle index generating function, you can compute all both the other generating functions. So for example, I claim that if you just look at f tilde of x, so f is any species, then f tilde of x, well, this is summation n greater than or equal to 0 Sn mod fn x to the n. Now let's compute this using Burnside's lemma. So this is summation n greater than or equal to 0, and then we have 1 over n factorial summation w belongs to Sn fn, maybe let's use sigma here, sigma, and what do I want? So I want to write x to the n, but now what I can do is x to the n, if sigma is in Sn, then I can write this as x raised to m1 sigma x squared raised to m2 sigma and so on. But that is exactly the same as zf x squared x cubed. So the type generating function is obtained from the cycle index generating function by just replacing x subscript I by x to the power I. And it's easy to see that this generating function is just given by zf of x comma 0 comma 0. I'll leave that as an easy exercise to you, because when you evaluate this type generating function, it's x2, x3 and x4 and so on to be equal to 0. You don't look at any permutations other than the identity permutation. Your permutation should only have one cycle, and so you end up counting the elements of Fn. Okay, so that's easy to prove. Now at the end of this recording, I just want to highlight one last thing, which is the Frobenius characteristic function. So this is a different, it's a generating function again associated to a species, and I will define it like this. So it's the sum over n greater than or equal to 0 of the Frobenius characteristic of the permutation representation C of Fn. So what do I mean by this? So firstly, let lambda hat denote the product d greater than or equal to 0 lambda d, where lambda d is the set of symmetric homogeneous symmetric functions in infinitely many variables of degree d. This you can see is in fact a ring. Okay, even though there are infinitely many non-zero homogeneous components allowed in an element of lambda hat, when you multiply two of them, you will only involve finitely many non-zero components. So this is a ring, a sort of completion of the ring of symmetric functions. And this characteristic lives here. And what do I mean by this characteristic of CFN? Well, Fn is a set with an action of Sn, and so I can think of complex valued functions on this set as a representation of Sn. So given an element sigma of Sn, I can act on a function. If X lives in an Sn set, then you just do this. And this gives you an action of, so in this case, I guess what I'll be doing is F sigma inverse of X. For all sigma in Sn, X belongs to Fn. And that gives you a representation of Sn. And now given a representation of Sn, recall that its Frobenius characteristic is given by, is defined to be 1 over n factorial summation sigma belongs to Sn. And then what you have is product I greater than or equal to 1, the power sum symmetric function pi raised to the power mi sigma, where again mi sigma is the number of I cycles in sigma. And this is defined in such a way that if you take the irreducible representation corresponding to lambda, then its Frobenius characteristic is S lambda. So for every partition lambda n, you take V lambda, the representation of Sn, its Frobenius characteristic is S lambda. So this is a homogeneous symmetric function of degree n. And this I call the total characteristic of the species F, the characteristic generation function of the species F. But from this definition, what you see is that the total characteristic of F is just ZF P1, P2, and so on. Indeed, if you take this thing, right, if you take this, then what is it? This is summation n greater than or equal to 0, 1 over n factorial, summation sigma in Sn. And then we have Fn sigma, and then we have P1 to the M1 sigma. This is from the definition of ZF. And so on. But this is just the trace. Oops, out here I forgot. In this definition, I want here the trace of rho sigma times, let's make it a little bigger. I forgot the main thing in this definition, trace of rho sigma, which the character of the representation. So it's the power sum symmetric functions, the weighted average, where the weights are the character of the representation. So this is the trace of sigma on the space C Fn. The trace of a permutation representation is just given by the fixed points. And that's, of course, by definition, the Frobenius characteristic of F. So now let's look at this example of the species S, where we computed the cycle index generating function. So we had Zs of x1, x2 is product of 1 over 1 minus xi, which means that characteristic of S is product of I greater than or equal to 1, 1 over 1 minus pi. If you expand this out, what you'll get is summation n greater than or equal to 0, summation alpha runs over all partitions of n, p alpha, where p alpha is the power sum symmetric function corresponding to the partition alpha. So p alpha is, maybe I'll just call it lambda. So p lambda is product over I greater than or equal to 1, pi raised to mi lambda, where mi is the multiplicity of I, the number of times I occurs as a part of lambda. So that's the characteristic of S. And let's try to expand this in terms of Schur functions. So we know from the representation theory of symmetric groups, or from the theory of symmetric functions, that the expansion of power sum symmetric functions in terms of Schur functions, the coefficients are given by the character values of the symmetric group. So let me just recall how this works. So what we have is, recall that p alpha, p lambda is given by summation over all partitions alpha of lambda chi alpha lambda s alpha. So what we get is that the nth Frobenius characteristic, the characteristic Frobenius characteristic of C of Sn, that is, if you let Sn act on itself by conjugation, and you think of that as a permutation representation, then its Frobenius characteristic is sum over all lambda partitions of n, and then sum over all alpha partitions of the size of lambda, so that's also partitions of n, chi alpha lambda s alpha. And if you interchange the order of summation here, what you get is this is sum over alpha partitions of n s alpha, and then you have sum over lambda partition of n chi alpha lambda. As a consequence, since this is the Frobenius characteristic of a true representation of Sn, each irreducible representation of Sn occurs in this with non-negative multiplicity. So as a consequence, we have summation lambda n chi alpha lambda is greater than or equal to 0 for every partition alpha of n, which is saying that the sum of every row of the character table of Sn is non-negative. So this is a weaker form of a theorem of a special case of a theorem of Solomon, who gives a result for the sum of a row of the character table of any group. And there have been lots of strengthenings of this result for symmetric groups due to Sheila Sundar.